Hello everyone and welcome to my channel. It's me Bikalpa. Today we are going in a live session where we will be implementing some of the basic data structures in Python. This will be actually part 1 of the different live series I will be conducting in the next few weeks. So starting the live session, actually I will talk about the outline of today's session. First of all, we will talk about BIGO notation. We will actually use this notation to analyze our algorithms, and we will then go on to discuss about dynamic arrays and then sets, hash tables, and stacks, linked lists, doubly linked list, queues, deque, and then finally binary search tree. We will cover these topics in this part, and in the next part we will start from here to implement more advanced data structures like heaps and tries and so on. So starting with the basic definition of data structure, data structures are actually nothing more than a way of storing and organizing data so that the operations like reading, searching, updating are performed on it efficiently. So there are different ways of storing data in our computer, but we want our way to be such that we want to have our update, delete and search operations as well as read operation very efficient. Today, first of all, we will begin our session by discussing about the BIGO notation. Actually, this is nothing more than just a way of describing how well an algorithm performs, either in terms of time, actually the run time it takes the algorithm to execute, or additional space an algorithm requires to execute, right? So it can be either time complexity or it can be either space complexity. So BIGO notation is generally used to analyze algorithms in the worst case scenario. That means when everything goes wrong, then what would be the upper bound of our algorithmic performance? So we will try to analyze that with our BIGO notation. So if I say an algorithm has O of n of complexity, then you have to understand that this algorithm will need at most n operations to execute. That is, n is the size of the input, that is the size of the problem itself, and you have to assume that the n approaches infinity. We will say that O of n is the complexity of the algorithm, where we are assuming that n is approaching infinity. Then when n approaches infinity, how many operations will the algorithm really need to get itself executed? So seeing some of the examples of BIGO notations, we can see an example here. Basically this is a Python function. This takes argument n, and for I in range n, we will just increment the count of actually the sum equals to sum plus I, and then we return s. So this loop runs for exactly n times. So we can clearly say that the algorithmic complexity, actually time complexity of this algorithm, is O of n. Let us see another example. Here we can see a function named search, and then we can clearly see that whenever we are passing a list named items, and then we are traversing for each and every item of that list, and if the item is equals to key, then we return true, otherwise we return false, right? So actually the item we are searching upon can lie on the first or the beginning of the items list, or it can lie on the end of the items list, right? But in the worst case, in the worst case, we will assume that the item lies on the very end of the list. So in that case, we have to traverse through each and every element or each and every item of that list, so that our loop runs for n times. That is in the worst case. So our BIGO notation of this algorithm will be O of n. So Daniel Thabamagar is here. He says hello. Hello Daniel. Pratigya is waiting. Pratigya, hello Pratigya. Sakin Mahajan, hello Shakin. How are you all? So let us discuss yet another example. Actually, I have a function named powers of 2 less than, and then I pass argument num. So actually inside this while loop, you can see the line while p equals to p asterisk 2, right? So actually in each iteration we are incrementing the size of p by 2 times, right? We are doubling the size of p, so that this particular loop runs only for 7 times when number is equals to 100, right? That means for num equals to 100, our loop runs for 1, 2, 4, 8, 16, 32 and 64. Those numbers get printed. It runs only for 7 times. So actually we can say that it runs for log of 2 of n times. The base is 2. When we say the algorithmic complexity is log n, we will assume that the base is 2. In computer science, we assume the base is 2, right? So this algorithm has log of 2 of n complexity, because at every time the input or the problem size is just reduced. It is just halved. So another example, in this function, actually we run I from 0 to n minus 1 and j from 0 to n minus 1. That means the outer loop runs for n times, the inner loop runs for n times. That means for each iteration of outer loop, we have inner loop running for n times. So our total algorithmic complexity will be O of n squared. And we can see here the square function. Basically, whatever we pass as the value of n, this function can just return n times n, right? It can just return the actual value in just constant time. Actually, the number of iterations does not depend upon the value of n. Whenever you pass 1 million, it will also take only one operation. And when you pass 1 billion, it will take only one operation. When you pass only 1, it will also take only one operation. So this will be a constant time algorithm. We represent a constant time algorithm saying O of 1. And then here is another example. Most of the time our students get confused for calculating the algorithmic complexity in this type of questions. Actually, here the loop is running for 100 times, actually 99 times to be specific. For I in range 1 to 100, we are running the loop here. But the number of times this loop runs does not depend upon n, right? Because if you pass n as 1000, this loop will run for 99 times, right? If you pass 1 million, and in that case also this loop will run for 99 times. If you pass 1 trillion, then this will again run for 99 times. So the number of iterations will not depend upon n, so that we cannot say this algorithm is O of n, right? So we will have to say that the algorithmic complexity of this algorithm is O of 1, because regardless of the value of n, the loop always runs for constant number of times. So let us look upon some of the complexity classes here. Actually, we have the best complexity, that is constant time, O of 1. That means for n equals to 1000, only one operation is needed, right? If we consider that each operation takes 1 millisecond, then we can say that the algorithmic complexity O1 will complete in 1 millisecond. So the next is logarithmic, that is log of n, that will take 10 operations for n equals to 1000 and then executes in 10 milliseconds. And then gradually, if we go downwards, our algorithmic complexity gets more and more, it gets increased, right? So linear time and linearithm time, quadratic time, exponential time. So we can see that as we go down the complexity class, our number of operations increases very rapidly, right? So linear for n equals to 1000 operations needs to get executed. For linearithm, it's 10,000 and 1 million. And when you go to exponential, it is 10 to power 301. That is a very, very, very large number, right? So if we consider the time, we can clearly see that when we reach around linearitmic complexity, it is already 10 seconds, right? 10 seconds for a single operation is quite big a time. So if for quadratic, it takes 16 minutes, and for exponential, it's about infinity. So it is our concern that we want to write algorithms that have very least time complexity. That means around constant time. Actually, it may not be feasible or possible to write constant time algorithms, but we would want to analyze our algorithms and increase its performance if it is possible, right? Sudeep Paudel says, La sayo feri pani dazu. Hello. Hello, Sudeep. Adipu says, hello, Dai. Hello. Suman Kharka. Hello, Bikalpa. Hello, Suman. How are you? And then we make some assumptions on big O notation. Actually, the constant terms and constant coefficients are not considered, because we are only really concerned about the upper bound, right? We are concerned about the highest order term. So for n plus 55 number of operations, we will say this big O will be O of n. We will just ignore this 55, right? So if we say 6n squared plus 80 operations are needed, and then the class will be O of n squared, because we will just ignore the 80 and 6 part. And then another assumption big O notation assumes is that when there are more than one terms, then the highest order term will be the algorithmic complexity. So here and log n, and there are 3 terms, right? But here the big O notation complexity will actually be n log n, because it is the highest order term here. In the second one, 6 sin squared plus n plus 80, actually the algorithmic complexity will be O of n squared, because it is actually the highest order term in our number of operations. So we can see that in this algorithm, actually a function, it takes n as an argument, and then for I in range n, actually this loop runs for n times. So this loop in particular will have big O notation algorithmic complexity of O of n. And then in the second part, we are running a nested loop here. This part in particular will have O of n squared. But when we have to determine the overall complexity of this algorithm, it will be O of n squared, because O of n squared is the higher order term. So we will just ignore the O of n part. We will say that this complexity is O of n squared. So let us try to set up the environment for today's session. Actually, I will create a desktop folder here. I will say is at data structures, and then basically I will open my terminal, open Visual Studio Code. Actually, I will assume that you already have Python and Visual Studio Code installed in your machine, right? So if you don't have it installed yet, you can just go to repl.it, and then you can just start coding. It is an online IDE, so you do not have need to have Python installed in your machine to follow me in this video. But actually you can install it later after this live session will be over, because this video will be public in YouTube whenever you want to watch it. So inside this repository, first of all I will want to create some of the data directory structure, like data underscore structures. All of my data structure code will go inside here. I will create a directory called examples. I will put the examples here. Let us create a git ignore, and then I will just open my terminal, python -m env, and I will create an environment, a virtual environment, and then activate it, source env being activate, and then I will just git ignore the env folder. Okay, also I will git ignore pycache folder, because it is not needed in the source control. All right, and then as I have multiple modules inside my project, actually I will have to install them separately using the setup tools, right? So I will create a new file, setup.py, and inside it, from setup tools, import setup and find packages. What I will do is I will set up name equals to data underscore structures, and then version equals to 1.0, packages equals to find packages. I will do this same for the examples directory, examples. All right, inside the examples directory I will create a file called init.py. Actually this will tell me that the examples directory is actually a Python package. So inside data structures also I will create underscore init dot underscore dot py. Okay, actually we have set up our coding environment here. So basically okay, one thing is remaining. What I will do is I'll just say pip install dot, actually I think it's -e dot. Okay, it has successfully installed examples. All right, so let me clear this, and then okay, So basically whatever we write today will go inside this data underscore structures module, right? So I will write all the code that belong to the data structure here, and then I will write the example testing code inside this examples folder. Actually this particular folder, data structures dot egg info, actually this is also not important, I will ignore it. Asterisk dot egg dash info. If you guys are doing following with this repl.it, I just told you earlier, then you would not have to do all these, right? Actually this is a common convention of writing a Python project. So here we go. So now let us come back to our data structures. We will first discuss the operations and theory part, and then we will go on to implement them on code. Okay. So dynamic arrays are very simple data structures. They are arrays. If you are a programmer, then you already know about array, right? Arrays are types where you actually store the data and you access them using index, right? They are stored in contiguous memory location. That is what we all read about in C programming or any other programming languages. They have arrays, right? But dynamic arrays are a special type of arrays that resize themselves when their capacity gets filled. So if it was a static array, suppose if I had a static array of 5 elements and then my array was my array was full, and then if I want to add another item, then I could not add another item, right? Because my array is full. But a dynamic array is a special array. When we try to add an element, the array itself is resized to contain a new size to be capable of containing the new element. And then similar to the arrays, the elements must be contiguous in memory. They must be contiguous to each other, and they are implemented by default as list type in Python. Actually Python is a very interesting language. It has already implemented the dynamic array as a list type in Python. So if you look at the applications of dynamic arrays, actually dynamic arrays are used wherever static arrays are used. We can use dynamic arrays too, right? So that will be a whole section of the application. But separately we can implement other data structures using dynamic arrays. Later on we will implement stack using dynamic array, and we will implement queue as well as other data structures using dynamic arrays. So dynamic arrays are the fundamental blocks of building some other important data structures. So let us go and see some example of dynamic array, right? I will create a file called dynamic array.py. So basically the Python list is called dynamic array. So I will just create a list called names and then put inside here John, area, Tyrion. Okay. So this is a list, a Python list, and in terms of data structure, it is a dynamic array, because if I try to find the length of the names and then print it, I will put it inside print statement. If I print it, then it will give me 3, right? Because the size of the array is 3. But now if I add names.append, append means adding to the last, right? So if I add names.append and then put something like net here and then print the length of names, it will now become 4, right? You can clearly see that earlier the size was 3, but later the size got increased itself, right? It resized itself and it becomes 4. So the algorithm to resize the dynamic array, it is built in inside the Python implementation, so we need not worry about that. Actually we can just use it as a simple array, but we can add as many items as we like inside it. Everyday Kerma says, hello Dai, hello brother, how are you? And then let us see some other examples. Actually inside the dynamic array we can access an element using an index, right? So if I say print names and then pass in 0 here, this will print me John, right? Because names 0 means the first element of the names array, so this will print me John. If I say names 1, then this will give me Arya. That is so obvious, right? If I say names -1, then it will give me Ned, because in Python we can index in negative way too. If we come from negative side, it will give the last element. If I say -2, it will give me second last element. If I say -3, it will give me third last element. So we can index from the reverse side also. So if you want to insert an item in the middle of the array, what you can do is names dot insert, and then you give the index. Suppose I want to insert at 0 index, and then I will insert something like Kathleen, and then I will print the length of names. It will become 5 because we have just inserted a new value, right? If we try to print names itself, we can see that it prints Kathleen, John, Arya, Tyrion, Ned. Actually, our earlier old array was just this part, right? So we inserted Kathleen at index 0, so it got inserted here, and our new array has become of length actually 5. So you can just remove an element just like so. You can names dot pop. If you do just like this, the last element will get popped, right? So if you run this, the last element Ned will get popped. But if you say names dot pop 0, then the first element will get popped. That means we had added Kathleen and we did pop 0, that will pop out the first element. Actually, you can pass any index here, right? So using this, you can actually implement dynamic array in Python. This is very simple. Looking at the algorithmic complexity, let us see the algorithmic complexity of dynamic array. Actually, it was somewhere here, wiki.python.org/moin/time complexity. I will put this link in the description, right? So in the documentation, we can see that the list has the average cache complexity for insert as O of n. This is because when we insert some element at some position, suppose I have inserted at 0, right? So basically all of the element after that index need to be shifted right by the position of 1, right? Because to create a blank space at index 0, all of the existing elements in the array after the index 0 should be shifted right by 1 position. So that means in the worst case, if we want to insert an element at the index 0, then all of the elements in the array should be shifted right. So it is clearly O of n. The same is valid for deletion. Actually, where is it? Delete item, right? It is O of n, because if you delete an item at the first index, then all of the other elements should be shifted back 1 position leftwards, right? Sudeep Podal says, what is the difference between pop and remove? Actually, pop will take argument as index of the element. So if you say pop 0, it will pop out the first element, Kathleen. But if you do remove, you have to pass the value instead. So if you say remove Kathleen, this will be the same because Kathleen was at the first index, right? So if you use pop, you have to pass the index, whereas if you use remove, you have to pass the value instead. So let us dive right towards another data type called sets. Sets are a unique collection of items. Every item in the set is unique, and they are not in any particular order. So a set can be unordered, right? And they are similar to sets in mathematics. In our basic grades, when we read set about mathematics, we used to say them as a collection of unique items, right, where the duplicates are not allowed. So the same is valid in Python too, and they are implemented by default as set data type in Python. So we can see some examples of set as a equals to 132, n equals to cab, and something like that. We can repeat the value here. When we see the operations in set, we can see the size operation returns the number of items in the set. and then union will perform the union operation between two sets. Intersection operation will perform the intersection between the two sets, and difference operation will compute the set difference between two sets. And exists, this function actually checks if an item exists in the set. And what are the applications of sets? If we see, we can apply sets to remove the duplicates in our data, and then we can perform set operations just like in mathematics, right? So it is very useful. We will see an example to remove duplicate later on. Okay, let's see how the sets work, right? Okay, sets.py. For declaring sets, actually you will have to use curly braces. So if I say names equals to, or I will say numbers equals to, okay, numbers equals to 44, 55 and 677, and if I say print length of numbers, it will print me 3, right? But if I say 44, 55 and then another 55 and 77, this will still be 3, because these duplicate items are not considered. They are not considered as two items, but they are considered a single item. So 44, 55 and 77 are the elements in this set. If you type to print numbers, you can see 44, 77 and 55. Actually they are not even in the order we inserted them, right? So they can be in any order, but this 55 cannot be repeated in our set. So we only have 155 occurrence in the set. Sabugiri asks a very good question. How can we know the time complexity of any Python program, or you say Python code? Actually, we will have to go through the code and see what are the different complexity classes of different operations we are performing, right? So we will try to individually see the complexity classes of those different operations, and then our total time complexity will be the maximum or the highest order complexity among those time complexities. So we will learn how to analyze the time complexity of algorithms later when we try to implement queues and stacks and all those. So we will come there later. That is actually a good question. Thanks, Sabugiri. So yeah, we can just print the length of numbers. It will be 3, because 55 is not considered 2 times, because it is a set, and set in the set all the items should be unique. So if I say if I try to print 55 in numbers, what will it print? It will print true, because the 55 exists in the numbers, right? If I say instead 99 in numbers, this will print false, because 99 does not exist in numbers. So there are various other operations in the set too. We will actually not cover all of them because we have really limited time, but we can see in the same page the set has the separate section, the complexity. Actually, if we try to do something like x in s, then it is a O of 1 operation. That means it is a constant time in average case, but in the worst case it is O of n. Union takes O of len s plus len t. That means s is the first set, t is the second set, and those two lengths will be added, and the overall complexity will be the addition of those two lengths. Actually, we can see the complexities of other algorithms here. You can go through it, but actually I will not go through them all. Basically that is set for you. So let us move on to the next data type, that is hash table. Before talking about hash table, actually I wanted to talk about an example of how sets can be really useful, right? So suppose I had text input by the user. So I would say text equals to input, right? And then the text will be a string, right? So if I want to split the string into the different words, then I will do words equals to text dot split, right? Yeah, so words will be a list, right? So in a list, that means in a dynamic array, duplicates are allowed. But if we have an necessity to find out all the unique words in input list, so that means we want to remove the duplicates and only find out how many unique words are there. At that time, the set is really useful. So we can say that unique words equals to, we create a set with words, and then we will print len of unique words and then print it. So basically it will ask us for an input. I will say father, son. This will say the unique words are 3, because the is repeated 2 times, it will count as only 1. So this will actually count the distinct elements or distinct words in an sentence you have input. So we can actually use set where we need to remove the duplicates in the data. Koho says a class method and property, what do you mean by them decorators? Actually, Python decorators are a very shortcut way of extending the functions. If you do add property before any Python function, then that means that function can be accessed just like a property of a class. Actually, we will come to that later. Okay, I will show you actually in the code when we will be implementing the stack. So for now, let's postpone that. I will come there later. Where I was in hash table. So hash tables are associative data structures that store key value pairs, and the index of array where the key values should be stored is uniquely identified a function that is called hash function. So hash function will take the key as input, it will perform on that key, perform some operations on that key, and it will compute the index of where that key should go to the hash table, right? So let's see an example. Suppose we have a hash function of hx equals to 7x squared plus 5x plus 2. Koho says, could you please show simple example of this? Actually, I will show you later when I implement stack, because these data structures I am talking about, they are already implemented in Python by as a default or built-in data types. So actually, I was not going deep into them. Actually, I will implement them later when we will implement stack queues and all of them. So consider a hash function hx equals to 7x squared plus 5x plus 2 and mod 5. Mod means a modulo operation, percentage operation. That means it gives us the remainder after dividing by 5. So if we insert 2 and ohm, actually 2 is the key here and ohm is the value. We will try to compute the hash value of 2. So we will pass 2 inside our hash function. So x equals to 2, and we will compute 7 times 2 squared plus 5 times 2 plus 2. And we will calculate the remainder of that division after 5. Okay, so we will calculate it to be 0. Then our 2 comma ohm will go to the 0th index in our hash table. So if we say insert 6 and lux, we will pass 6 inside our hash function. This is the key, right? So we will calculate the hash. 7 times x squared means 7 times 6 squared plus 5 times 6 plus 2 mod 5. That will actually be equals to 4. So our 6 comma lux will go to the 4th index in our hash table. So if we see that, we can clearly see that the insert operation in hash table is O of 1, right? Because if you are given a key, you pass it to a hash function, and that hash function basically just returns you the hash value, and you can go to that index in your hash table. You don't have to start from the beginning and traverse one by one, right? You can just directly access the 4th index of the array of the hash table, and then you can insert it. So this will clearly be O of 1. If we had to, for example, traverse through each and every element for returning to the last index, then it would be O of n. But right now we need not do that. We can actually directly access the 4th index, so it will be O of 1. So suppose if we want to find the 6th key in from the hash table, right? If we have a hash table here, we have already constructed a hash table. Now we want to find what is the value of the key 6. So in that case we will first of all calculate the hash again. So the 6 will go inside the hash function, and we will calculate the hash function hash function of 6 will equal to 4, and we will go to the fourth index in the hash table right here, and we can find that the value exists here. We can take out that value, and we can clearly see that the value of key 6 is locks. So we can clearly see this operation is also O of 1, because we can directly access the hash value, and we can directly access the index of where that key is stored in the hash table. So let us see the removal. If you want to remove the 6 key from the hash table, so first of all you will have to calculate the hash of the 6. So that will be equal to 4, and you will go to the fourth index of the list or the hash table, and you will just delete that, as simple as that. This will also be O of 1, because you are just computing hash function, you are just accessing it, and then you can delete it. You don't have to go from the beginning to the end, right? So this is O of 1. But those O of 1 operations are actually conditional. That is, if we consider that there are not hash collisions in our implementation, right? So what are hash collisions? Actually, sometimes more than one key may be mapped to a same hash. For example, if we consider the same hash function hx equals to 7x squared plus 5x plus 2 mod 5, then we can clearly see that if we pass 2 inside it, it will give us 0. If we pass 7 inside it, it will give us 0, right? So first of all, if we inserted 2 like this previously, if we had already inserted this, then later if we try to insert 7, then we will see that the index 0 is already occupied, right? So there is a hash collision. Hash collisions may be resolved using either chaining or probing. They are actually very well known algorithms for actually resolving the hash collision, but we will not go through them because hash tables are implemented by default in Python. Actually, Python is a very amazing language. It already has what is useful for us implemented. So one thing we should always be careful about is we should always choose a good hash function which results in the minimum number of collisions, right? So if we had chosen a different hashing function, then we could have prevented this hash collision at all. So actually in Python we will not go on to implement the hash table or go on to see or analyze the hash functions and choose the hash functions, but you have to keep it in mind because this will clearly be important for you in the technical interviews. You will be asked these questions in technical interviews. So if we see the operations in hash table, we can see that the insert operation will take O of 1 time. We already have seen that. Remove operation will also be O of 1. Exists, it will be O of 1. Actually, exists will give us whether the key exists in hash table or not, and then update will be O of 1, as well as get will be O of 1. So these all will be O of 1, but these are with the assumption that the hash function chosen is sufficiently robust to avoid hash collisions. If there is hash collision, then this will be O of n in the worst case. Okay. So the applications of hash table are to store the key value pairs for efficient lookup, right? So we clearly see that if the hash table is implemented correctly, the hash function is optimal, then we can access the elements in O of 1 time, that is constant time. We can insert in constant time, we can search in constant time. That is really useful and that is really helpful. So let us see how hash tables are implemented in Python. So I'll create a hash table .py. If you have not already guessed, the dictionary data type in Python are the implementation of hash table in Python. So the dictionary default data type is the default implementation of hash table. I will show you how. Suppose I have a dictionary called table equals to, and then I say 1 and then colon. I will say my name. I will say 2 and then colon. I will say something like quotes. Okay, so this is a hash table. 1 is a key, 2 is a key, and then Bikalpa is a value, a quotes is a value. So actually the hashing part and then the storing part, these all are implemented by Python itself, so we need not worry about that. If we want to access the value inside the key 1, then we will simply do print table, and inside it we pass the key, right? Our key is 1. If we say 1, then the key is 1, the value is Bikalpa, it will print Bikalpa. Okay, if we want to insert a item inside the hash table, you will just do something like table and then 3 equals to, I will do something like YouTube, and then if I try to print table, you can see that inside 1 key there is a value of Bikalpa, the key is 2, the value is codes, the key is 3, the value of YouTube. We need not worry where they are stored, right? They are stored optimally, and Python does that work for us. Actually these keys can be anything, not just numbers, right? So I can have something like names, a name equal name as a key, and then Bikalpa as value, and then I will say profession as codes, and then I will say inside the table with the key of platform insert YouTube. So if I say these things and print table, the name is Bikalpa, profession is codes, platform is YouTube. So this is the hash table for you. Actually, if you want to see the implementation details of the hash table, you can see what I already talked about, right? So if we want to look if the key exists in the hash table, then that is in average case O of 1, but if that is in the worst case, that is O of n, because if there are very large number of hash collisions, then that hash collisions need to be resolved linearly. So the copy will be O of n, because we traverse through each and every keys of the hash table, and then we copy the key from one hash table to another hash table. Get is O of 1, we have done here. Actually I had done earlier. If I say print and then name, this is basically getting the value associated with the key name, right? It will give me Bikalpa. So yeah, deletion is O of 1, set is O of 1, and iteration, that means for traversing from key by key, that is O of n. That is quite obvious for us. So this is the time complexity of our hash tables. So let us go towards stacks. Up to now we have already discussed about 3 data structures, the dynamic array, the sets, and the hash tables. These 3 data types are implemented by default in Python, so we did not go quite deeper into them, but now from stacks we will try to implement them on our own. So actually these data structures and the algorithms are very important for you at different places. For example, if you are a student of a computer science, then you will be asked about these questions in your university examinations, and if you are seeking for a job and your employer will ask you in the technical interviews, and actually you may need to implement these while you are coding too. So yeah, these are very important, and I will try to show you the applications of these data structures too. So talking about stack, it is a single int data structure that follows LIFO. LIFO means last in first out principle. The item that gets added last will be the item that will be removed first. As an example, you can consider a stack of plates piled at a table. So if you bring a new plate, if you bring a new plate, then you will put it on the top, right? So you bring a new plate, you put it on the top. You bring a new plate again, you put it on the top. So when you are you put on the top, but when you want to remove a plate, you remove from the top again, right? So the plate you had added at the last will be the first you will be removing. The same is the condition for stack. You will add at the top and you will remove from the top. You can see a simple stack here. You can add and you can remove. The addition will be on the top of the stack, the removal will be from the same top of the stack, same end of the stack. So if we see the operations in a stack, the push operation, it adds an item in the stack. A pop operation, it will just remove an item and return to you. And pick operation, actually it will remove whatever it is on the not remove, actually sorry, it will return whatever item is on the top of the stack but without removing it, right? If we want to see what is on the top of the stack but we do not want to remove it, then basically pick is for you. So let us see how these push and pop and pick operations work. Suppose I have to empty stack. If I say push A, it will push A into the stack. If I say push B, then B will get pushed into the stack. See here, B is on the top of the A, right? So if I try to remove, the B will be the first one to be removed because A is already on the bottom level, right? We cannot remove the bottom element. First we have to remove the top element, and then only we can remove the bottom element. If we say push C, then C will be again stacked on the top. So the top of the stack will contain C. You can clearly see that the push operation is O of 1, right? Because you are basically accessing the stack, be it a linked list or a array. We will actually see the implementations later, but you have already a good access to it, and then you just go and insert the value there, right? So it is O of 1. You do not have to traverse the stack at all. So if we say pick, then it will not remove C, but it will return C. So you will have C as your return value, but it will not remove C. This is also O of 1 operation because you can just instantly see what is on the stack top, right? So if we say pop, on the first stack, then it will give us C, and then the first that means the top of the stack, and the C will get popped out. If we call pop again, the B will get popped out and it will return us B. If we say pop again, the last element A will also get out and it will return us A. This is also clearly O of 1 time, right? Because when you pop, you just access the top of the stack and you just remove it, right? So you need not traverse the stack as a whole. So we can clearly see push and pop and pick all are implemented with O of 1 algorithmic complexity. So we can see the stack has different applications. Actually, when we have to convert infix expressions to postfix expressions, that happens in the compilers, as well as our computer computes the expressions using postfix expression, right? So that conversion takes place using the stack. In the programming languages, the implementation of recursion also takes place with the help of stack. The call stack is implemented with the help of stack. The backtracking algorithms use stack by default. Explicitly they use stack. We can see the brackets matching problem. That means if we have opened a bracket, then there should always be a closing bracket. So that check can be done with the help of stack. I will show you how later on. And then the depth first traversal in trees and graphs, they are implemented using stack. I will also show you this in code also, and in visually also, how we can do depth first traversal in trees and graphs. So let us go on to implement the stack now. Actually, this is the first data structure that I will be implementing from scratch. So let us go to the data structures directory and create a file called stack.py. Okay, first of all, I'll create a class and then a constructor. So inside the constructor, actually I will be implementing the stack using the default list data type in the Python. So I will say self.items equals to an empty list. Okay, if you are familiar with Python, you should immediately understand this. Items is an empty list. It is a member variable of this class. So yeah, our size will be, I will write the separate class for size. So actually someone earlier asked how to use property, right? So if I want to write a function called size, and return self, actually len of self.size, self.items, right? So this is a this is actually a method inside the class, right? So from outside the class, you will have to do something like stack equals to stack, and then stack dot size, right? You have to keep the parenthesis. You have to access it as a method, right? But if you want to make it a member property of the class, you can just do property here. Now you can access it using like this stack.size. the Python will treat this function just like a property, just like as you would access stack.items, because items is a property, right? Items is a instance variable. You can also access size as a property. That is what the property decorator will do. And then you talked about class method too. Actually, a class method is slightly different than these class these normal methods, because inside these normal methods we pass first argument as self, right? This self is the instance of the object which is calling this this method itself, right? This is just like the this pointer in C, C++ or Java. Actually not in C, C++ or Java. So if we do something like class method, then we will have to write a function, but inside it the class itself will get passed, right? If we do something like that, then CLS is not the instance of the class, but it is the class itself. You can create even a new object like CLS and like this, right? Because CLS itself is a class. Actually these will not be quite useful right now here in stack, so I will just delete it, but I will keep this property because I want to access the size property using stack.size. So let's write def push. So pushing it just self.items.append, right? So self.append items.append, and then I will take second argument as item, and then I will append item. Okay, this function will push the item to the stack. Okay, and def pop self item. Basically, before writing the pop, I will try to write def is empty. This will check whether the stack is empty or not. I will just say return length of self.items equals to 0 or not. If length of the self.items, that means this list is list has the length of 0, then is empty will return true, otherwise it will return false. So before popping the item, I will actually try to check if self.isEmpty. If this stack is empty, then I will not give the user to pop from the stack, right? So I will say raise runtime error. I will raise an error saying that the stack is empty. Else, what I'll do else, I will just return self.items.pop. Actually, we had already seen inside the dynamic array here that I actually deleted it. We have inside the default list type, we have a pop function, right? So that will basically remove the last element of the array itself. So and this will remove the last element of the items, and it will return. So pop will return the last that means the top of the stack. Actually, we are assuming that the last element is the top of the stack. So whenever we add an element, we add to the last of the list, and whenever we remove the element, we remove from the last of the list. So we are assuming that the top of the stack lies on the very end of the list. So I think we have another operation remaining here, that is pick. So for pick, I will first check if stack is empty. Then I will raise value, that's a runtime error. The stack is empty. Else I will return self.items and then -1. If I do -1 in a list, in Python list, that means I am trying to access the last element, right? So in Python you can do negative indexing too. So if I do self.items -1, this will give me the last element in the list. This will just return the last element in the list. Actually this will not remove the last element, but this will only access the last element. And basically we are trying to do the same thing when we are trying to do pick, right? So yeah, this will be the stack for you. Okay. Pick will not have item, and pop will also not have item. Okay, only push will have item. If self dot is empty, this self is not needed. Okay, so go to the examples here, and I will create a file called stack.py, and I will just import this class from this file. So for that I will have to say from data structures dot stack import stack, right? We could do these because we had already, if you remember, we had setup.py already written. So this would install data structure and examples as modules inside our project, and they are already added to the Python path, so we can access them from inside here. So first of all I will say stack is a object name, and I will create a new object of class stack. So stack is a new object, and I will try to say stack dot push. I will try to push A. Stack dot push, I'll try to push B. And then actually I want to write a new method here, display. I want to display the stack. So this will basically traverse through self.items and then print it, right? So I will say print the contents of stack are, and then for item in self.items print item and ind equals to space. That means after each item a space should be printed. So coming back here, I pushed A, I pushed B. If I do stack.display, I can see A and B here, but it says cannot import name stack from data structures, data underscore structures. Data structures stack, here it is stack. So why could I not import it? Actually I was not activating the virtual environment, was it? I think that was the issue here. I don't know. cd.ls, cd data structures, cd examples, and python stack.py. Okay, the content of the stack are A and B, right? Actually this was not being able to import because I had installed these two modules inside my virtual environment, and I wasn't actually activating my virtual environment in that terminal. So right now I have activated my virtual environment and it is now working. So yeah, if I push A and push B, and you can clearly see that the contents of stack are A and B. Now I will try to pop a value, stack.pop, and I will try to print it, stack.pop, and print it, and then the stack.display. Sorry, I will not use this from now on. That is causing the problem. I think if I go here and select my interpreter as this one, this would be working. Yeah, this is working now. I have just selected the interpreter to be the Python inside this environment. So yeah, that works. Now we can see that when we print stack.pop, it prints B, right? Because B is on the top of the stack. I had added B at the last, but it will be the first to get popped out, and then if I display the stack, it says A. But if I had not done pop but instead done pick, then in that case B will get printed, but the stack is still A, B, because B is not removed, it is only accessed, right? Pick means only to look open but not removing. So I think, yeah, stack, we implemented a stack. Let's move on to another data structure, that is the linked lists. Actually, this is one of the very important data structures in whole data structure algorithms world, and in interviews too. So let us see what linked lists are. Linked lists are sequence of nodes where each node stores some data value and they have a link to the next node. The address to the next node or the pointer to the next node is in the node itself. So unlike array, these elements are do not have the necessity to be stored contiguously in the memory. If it was in the dynamic array, then these needed to be stored contiguously in the memory, but we need not store the nodes in the linked list contiguously in the memory. The list is represented by the pointer to the first node, that is the head pointer, and by using the head pointer we can basically access each and every element in that list. We can just traverse through the list. If we see the node of the linked list, then we can see that it consists of a data and it consists of a next pointer. So this next pointer points to the next node in the linked list. So if we have a reference to a node, then we can immediately access the next node by using this next pointer. So if we look at the operations in the linked list, we can list out these operations. Insert front, this will insert the item at the beginning of the list. Insert back, this will insert the item at the end of the list. Insert after, insert the item after the item 1 in list. That means item 2 will be inserted after item 1 in the list. Update item 1, item 2, this will update the item 1 to item 2. Remove item, this will remove the item from the list. Remove underscore front, this will remove the first item in the list. Remove underscore back, this will remove the last item on the list. And traverse, this is basically traversing through each and every nodes or each and every item in the list. So let us see how we can insert in the front of the linked list, right? So here is the algorithm. So first of all, we will assume that temp be a new node. We will create a new node, and then we will just say temp.data equals to item. That means we are trying to insert the item, so we will initialize that node to consist data as the item. So we will say that node temp.next, it points to head, and then the head will be shifted back to temp. Let us see this visually. If we want to insert m to the front, first of all we will create a new node, and then we will put the data inside it as m. Then we will say that the next pointer of this new node will point to the current head, and we will say that the head now points to the new node. So this has already inserted the m node in the beginning of the list, right? So we can clearly see that this is O of 1, because if this list consisted of 1 billion number of nodes, then also the same number of operations need to be executed. If this list consisted of 1 trillion number of nodes, also the same number of operations needs to be executed. So this is clearly O of 1. So let us see how we can insert at the back of the linked list. The algorithm is, we will first consider a new pointer that will point to the head, and we will try to traverse through each and every node of that linked list until and unless we find that trap.next is not null. That means we will go to the last element of the linked list, and then we will create a new node. Let us say that the new node is called new. then we say new dot data equals to item. That item is the item that is needed to be inserted. New dot next is null, and then we will say that the trap dot next is new. That means the last element, the last node will have its next pointer pointed to the new node. Let us see this visually. Suppose I want to insert m at the back of my linked list. So I will first create a new pointer trab, and I will just basically traverse through the index, through the nodes of the linked list. First of all, I will check, is this node the last node of the linked list? Right now, no, right? Because the last node of the linked list will have its next pointer equals to null, right? So this node in particular doesn't have its next pointer set to null, so we will not stop here, we will go to the next node. So trap will now proceed to next node. So is this node the last node of the linked list? No, because this doesn't have null in its next pointer. So we will basically go to the next node again. Is this node the last node of the linked list? Yes, because the next pointer has null, right? So we stop here. After that, we create a new node. We add the value, this m, to the new node, and we will say that the next pointer of this new node will be null. After that, we will point the next pointer of this last element to the newly created node. After that, we can clearly see that our element m has already been inserted inside the linked list. If you see this, you can clearly see that the algorithm is O of n, because if this list was 1000 items long, then to reach the end of the list, you have to travel through each and every 1000 nodes, right? If the list consists of 1 million nodes, then you will have to traverse through all of the 1 million nodes to reach to the last node. So you start from the head and you traverse through each and every node to reach the last node. So you will have to traverse through n nodes, and then you have the overhead of n operations, and this algorithm is clearly O of n. Let us see another algorithm. This algorithm is for inserting after a particular item. That means we want to insert item 2 after a particular item 1, right? So first of all, we will follow the same approach. We will create a new trap pointer and initially say it points to the head, and we will traverse through each and every node until and unless we have reached to the item 1, right? That means while trap data is not item 1, we will just move the pointer to the next node. And then finally, if we have reached the item 1, then we will stop there, and then we will create a new node. We will say new dot data equals to item 2. This item 2 is the item to be inserted. New dot next equals to trap dot next, and trap dot next equals to new. Actually, if we see this visually, you will have a very clear understanding. Let us say I want to insert p just after b, right? So first of all, we will have to traverse through entire linked list to search for b, right? So first of all, I will create a new pointer trap which points to the head. Does this node contain b? We are searching for b first, right? So does this node contain b? No, it doesn't. So we have to go to next node. Does this node contain b? Yes, it contains b. So we stop here. Then we create a new node. We need to insert p, right? So we insert p into that new node. Now we will point the new node's next pointer to the node just after b, right? So initially b had its next node as c, but now p will have next node as c, and then we will point b's next as p, right? So b will have p as its next element. So we can clearly see that we have inserted p after b. We can clearly see this is O of n algorithm again, because if we are trying to search through a node in a linked list, and that will always be O of n. For example, if right now b was at the second position of this linked list, right? Suppose if b was on the 1 millionth node of this linked list, then we will have to traverse through each and every element of those million nodes and then only reach b, right? So we are traversing linearly, so this algorithm is O of n for obvious purposes. So let's see another algorithm, remove front, right? So for this algorithm, we will first hold the head node in a pointer called temp, and we will just say head will point now to head.next, that means the next element, that is second element, and then we will just delete the first node. Let us see this visually. Suppose we want to remove front, we will create a new pointer. This will point to A, and then we will say head now points to the second element, right? It points to the next element, and basically we just delete A. Now head points to B, that means the first node is already deleted. So if you see this, this is clearly of one algorithm, because whatever the size of the linked list, the number of operations will always be equal. We need not traverse through a sequence of linked list to go to the end of the linked list. So let us say we try to remove from the back of the linked list, right? So for that we will have to traverse each and every node to reach the second last node. Actually we will not reach the last node, because if we delete it, we will have to set the second last node's next pointer as null, right? So if we already reached the last pointer, there is no way we could come back, because the links in the linked list, in the simply linked list, are always in the forward direction. So if we go to the M, there is no way of coming back to C, because we can go from C to M, but we cannot go from M to C, right? So we will have to stop just one position before we are removing the item. So we will reach to the second last node, and then let S last be the second last node. We will just say hold a pointer that will point to the last node, and we will just say second last dot next as null, and then we delete the temp. Looking it visually, we can see first of all we create a pointer trab at the head of the node, and now we will try to see if this is the second last node, right? So how will we know if this is the second last node? For that we will try to look upon the next element, and if we see the next element is null, that means if the if we try to see the next element and the next element, sorry, we will try to see 2 times next, right? So if we see next and next, if this is null, then we will clearly know that this will be the second last pointer. But right now this is not null, so this is not second last pointer. Now we will move forward. So this is the second last node of the linked list? Then we will try to check. For that we will go to next and then see the next. This is not null, right? So no, B is also not the second last node. Again we go to the next node. It's C the second last node. Let us see. First of all we will try to go to the next node and then see the next pointer. It is null, right? So yes, we have reached to the second last position, second last index. Now we will stop here. Now we will create a new pointer called temp that will hold the that will point to the last node, right? And we will say trap.next equals to null. That means we will just store null at trap's next position, and then we will basically delete the temp because it is no longer connected to the linked list. We can safely delete it. We can clearly see the remove operation is of n, because we have to go from the first of the array to the last of the array. We have to travel through each and every node in the array in the list, so it is clearly O of n. So let us see how we can remove an item. So for removal, let's see how we can do it. First of all, we define a pointer to the head, and then we will try to see if we have reached to the item just before an item, right? So if we try to delete B, we will go and stop at A. If we try to remove M, we will go and stop at C. We will try to stop at just one node before that node to be deleted. So for that we have this while loop, and then we will store the node to be deleted with a temp, and then we will say that trap.next equals to trap.next.next. Actually you will see this visually later, and then we just delete temp. For example, if we want to remove C, first of all we create a pointer that points to the head, and then we basically traverse until and unless we reach to the node just before C, right? So how will you know that we have reached just before C? For that we have to check the next pointer's data, next node's data. So for B, let's see the next node, and in this node the data is C, so that we will know that we have already reached to the node just before C. So we will now stop here, and then we will try to hold the reference to this node in a new variable called temp, and now we will say trap.next equals to trap.next.next. That means trap will now point to the element just after the node to be deleted, and now we can safely delete temp. This is also O of n, because in the worst case, if the item to be deleted is towards the last position, right, in the second last or the last position, then we will have to traverse through each and every nodes in the linked list to reach to that item, and that is clearly O of n. So let us try to implement the linked list. Actually, this will be quite fun, I think. Let us create a new file, linked underscore list.py. So inside here, first of all, I will create node, right? So for the node, I will say class node, and inside it I will define a constructor. So what are the elements that is inside the node? Actually, if I remember, it is self.data. Let's say self.key. Okay, self.key. Let's say data. Actually, I prefer key, but I have already explained you saying it as data, so I will put it data here. I will say self.data equals to none, and self.next is also none. We do not have null in Python. Null means none in Python, right? So actually we will try to receive an item from the node constructor itself, and we will try to initialize the data with item. Okay, this will be more easier because we can just pass an item to the constructor, and then we will have a node created. So yeah, this will be a node for our linked list. So I will create another class called linked list, and inside it I will what we have inside linked list is I will have head equals to none. Basically, before we even start with the linked list, we have an empty linked list, and that will have its head pointer pointing to null, right? So it will be null. And then right now I think that's it. Okay, now I will write insert underscore front. I will pass an item here. So if we try to insert to the front, first of all I will have to check whether the linked list is empty. Okay, so I will say if self.head is none, that means the linked list is empty, right? I will put comment here. If the linked list is empty, the self.head will be none, right? So in that case, I will say self.head will be a new node. I will create a new node and pass item to it, this item inside the constructor. So if not, we are trying to insert at the front, right? So inserting at the front is I will say node equals to a new node, and then I will say node dot next will be head, and then I will say head equals to node itself, right? Because I will have to create a node here, and then that node's next will be the existing head, and the head will be the new node. The newly added node will be the new head, right? So let me put some comments here. Create new node and make it head, right here. create new node, and node dot next equals to head, that is existing head, and now I will say update head to be new node, right? So new node will be the head now. Okay, that is inserting at the front. Actually, let's just go on writing and testing, right? Because if we don't test, we may have confusion later on. Inside example, I will say linked underscore list dot py, and from data structures dot linked lists, I will input linked list. So I will say I think I will create names or fruits. Okay, fruits equals to linked list, and I will say fruits dot insert at front, I will insert mango, right? I will try to run it successfully. If it runs successfully, then there is no error, right? Okay, it runs, so there is no error. Okay, I just remembered I want to store the number of items in this linked list. So inside the constructor, I will create a new property called self dot num items, which will initially be 0, and then I will, after inserting a node, I will just say self dot num items equals to self dot num items plus 1, right? After inserting every element, I will just increment this count, and then I will just say def is underscore empty, self is this linked list empty. For that, I will just say return self dot head is none, right? If self dot head is none, then the linked list is empty, right? Because if head is null, then that linked list is obviously empty, right? So yeah, and I will try to define another method called display. So we begin from we will begin from self dot head, right? This is a pointer, creating a new pointer. Then I will say while we reach to the end of the list. So while trab is not equals to, or trab is not none, while trab is not none, I will just say print trab.data, and end equals to, I will put an arrow here, and I will say trab equals to trab.next. I will print that particular node, and I will move to the next node. I will print that particular node, and I will move to the next node. Okay, so printing the data at current node, and then moving to next node. Okay, and at the end I will just print a new line. So if I go here and then I print actually do fruits dot display, this will print mango, right? Because I have only one item in the linked list. So let us try adding another. If I say fruits dot insert front, I am inserting at the front, right? So orange, this gave an error. Node is referenced before assignment, actually at line number 32. Let's see what's the matter here. Okay, I created node, and then inside node I passed node, but I have to pass item here because item is passed with the insert front as an argument. So go to this example and run it. Head referenced before assignment, line number 33. Let's see. 33 head. Okay, this is not head, this is self.head. for accessing the property of a Python, you also you always have to use self, right? Because head is a different quantity, self.head is a different quantity. So go back and run it. Okay, we can clearly see orange has been added just before mango at the beginning of the linked list. So let us go on to remove from the front. Okay, def remove underscore front self. So first of all, we will try to check if self dot is empty. That means if the linked list is already empty, then we will not be able to remove from the front. So we will just raise an error, say runtime error. The linked list is empty. Okay. But if not, then we will try to remove the first element, right? So to first remove the first element, we will have to store the reference to the first element in a temporary variable, right? So I will say temporary variable temp equals to self.head. Temp will actually store the value of head, right? So I will do self.head equals to self.head.next. Actually, I will not this temp also, because in Python we have a default by default garbage collection, and that garbage collector will do the work of deleting the node for us. So we will not be concerned about deleting that node by ourselves. So yeah, I think this will be fine. Let's see. I say fruits dot remove front. If I remove from font, I will have to display it too. First dot display and then run it. Okay, the orange has been removed, right? It has been removed from the front. This always asks me. Okay, I will say yes. So yeah, we have all successfully removed from the front. If we try to comment this out and then remove the front, we will have to get value error. The runtime error. The linked list is empty, right? Because we have defined it here. If the list is empty, then we will just print out the list is empty. So let us write diff remove underscore back self. So we try to remove the element from the back of the linked list. So for that, we will try to look upon the different cases. If self dot head, basically first of all let's check self dot is empty, then just raise runtime error. The linked list is empty. Elsewise, if self dot head dot next is none, then that means the head itself is it is the only existing node in the linked list, so that we will have to remove the head. For that we will just have if the self.head.next is none, that means the head doesn't have the next element. The only node in the linked list is the head. Then we will just say self.head equals to none, right? Because we just tell that the head is now none. Else we will create a trap pointer which will be self.head, and then we will move on to the second last element, right? So if we want to remove the back, then we will reach up to the second last element. So while trap dot next dot next is not none. Okay, for that I will just say trab equals to trab dot next. Okay, after that we have reached to the end of the linked list. Then we will basically say trab dot next equals to trab dot next dot next. Okay, I think this will work. Let's see. I will insert mango and orange, and finally I will fruits dot insert. Was this remove back? Okay, I will do remove back, and then I will fruits dot display. Okay, orange and mango, and we removed the last node and we only have orange now. So we removed the last element from the linked list. That is fine. Let's try what we have tried. Remove front, remove back, insert front. Let's try insert back. Insert back. So for inserting at the back, we will basically first of all have to reach to the last node, right? So to reach the last node, what we have to do is first of all we will try to check if self dot head is none, or we can just say self dot is empty. That both of them are same. If self dot is empty, that means the list is empty. That means insert back is also inserting the element, the node in the linked list itself. So we will make self dot head equals to node item. Insert back will create will receive an positional argument here, item. Okay, this means if the stack is empty, we just create a new node and make it head, right? If the linked list is empty, create new node and make it head. Okay, else if it is not empty, then we'll create a pointer called trap. This will be self dot head, and from the beginning of the list, that means from the head, we will just traverse, while trap dot next is not none. That means until and unless we have not reached the last element, right? So while we have not reached the last element, trap dot next is not none, we will just say trap equals to trap dot next. That means we are just go to the next node. Okay, at this point we have already reached the end of the linked list, right? So we will just have to create a new node with item, and then we will say node dot next equals to none. We will not have to do that, I think, because we have already defined self dot next equals to none in the constructor of the node itself. So I will not do that here. We can skip this. Node equals to node dot item, and then I will say trap dot next equals to node, because the trap is the existing last element. We have created a new node. Now we will point the next pointer of the existing last node to the new last node. So if we do this and try to test it, let's see. Fruits that remove back, I will just comment it, and then insert underscore back fruits dot insert back. I will insert apple. That should be inserted at the end of the list. Okay, orange, mango, and apple. This is added to the end, right? So basically, how many methods we have written here? Display is empty. Insert front, insert back, remove front, and remove back. Okay, those were pretty easy. So let us see how we can delete at a particular index. Actually, I think I won't do that here because I will give that as an practice, as an example, as an exercise to the viewers, and we are quite short on time too. So let's move on to the next topic. I think it's pretty easy to insert at an intermediate node too, because you just have to go to the node just before that intermediate node and then delete that node. So yeah, we implemented the linked list. So let's go on to the next data structure, that is the doubly linked list. Doubly linked lists are quite similar to singly linked list, but the only difference is that the nodes will contain 2 pointers. It will have a link to the next node as well as the previous node. You can see here this node has 2 links, previous and next. This B node has also 2 links, previous node and next node. C also has 2 links, previous node and next node. So there are 2 pointers, head and tail, that are tracked in the linked list and that point to the first and last node respectively. So head points to the first node, tail points to the last node. So we can see the single node here, it will contain data, it will have a previous node prev, and it will have a next node next, and its node stores data, prev, and next. Next points to the next node, prev points to the previous node. So the operations in the doubly linked list are insert front, insert back, insert after. These are very simple, similar operations to the singly linked list, right? So remove front, remove back. We have traverse forward as well as backwards. Actually, in the singly linked list, we could not traverse backward, right? Because we had only unidirectional operations, unidirectional pointers. But now in the doubly linked list, we have opposite direction pointers also, so we can traverse in the backward direction. So let us see how we can insert an element on the front. Actually, this algorithm is quite gibberish. You can look on to it later. I will just explain you in visual terms. So suppose I want to insert front, insert M at the front of this doubly linked list. So first of all, I will create a new node to store M. Then I will say the previous pointer of M will be null. I will say next node of the M will be the current head, that is A. I will say the A previous pointer will point to M because M is the new head now. And I will just shift the head pointer back to the new node. So now our node has already been inserted into the linked list, doubly linked list, and this algorithm is clearly O of 1 because it is constant time. No matter how many nodes are there in the linked list, the number of operations will always be same. So let us see how we can remove from the front. First of all, we define a pointer called temp that points to the head, and then we will just point head to the next element, that is second element. We will just shift the head pointer to point to the second element, that is saying the second node is now the head, and we will just say the second element's previous pointer, it will be null because after the deletion the head will have a previous pointer pointing to null, right? So we will have head's previous pointer equals to null, and we will just delete the temp and it will return us M. This will clearly be O of 1 time because no matter how many operations are there, how many number of nodes are there, the number of operations will always be similar. So insert back, to insert at the end of the linked list, we will just create let us just skip these. gibberish algorithm. Just see it visually, right? So we will insert the m at the back of the linked list, okay, the node m. So first of all, we will create a node m. For inserting at the back of this linked list, we now do not have to start from the beginning and then go to the end of the linked list, because in the doubly linked list we already have a pointer called tail, right? So this will always be pointing to the last node, so we can directly access, we can instantly access the last node of our linked list. We will not have to go from the beginning and then traverse each and every node, right? So for that we will create a new node called m, and then m's next pointer will be null. The previous of m will be the last node of the existing linked list, and then the existing linked list last nodes next will point to the new node, and we will just bring that tail to the new node. So this will be the new tail now, and we have successfully inserted this element, this node at the end of the linked list. This algorithm is also O of 1, sorry, it is constant time. Actually, if you remember, in the singly linked list the insert back operation was O of n, but in doubly linked list we have O of 1, because we already have the access to the tail pointer. So let us see how we can remove from the back. First of all, we hold the last node with a temp pointer, and actually we do not have to go from start from the beginning and then go to the end, because we already have the reference to the last node in our doubly linked list. So we will just say that the second last node's next element will be null, and we will just make the tail point to our second last node. Now we can safely delete this last node because it is no longer needed, and this will return us m to us, because that was the element to be removed, right? So whenever we remove the element, we just return it back, so it will give us m back to us, and this will clearly be O of 1. So let us see how we can insert after a particular item. Suppose we want to insert m after b. So we will start from the beginning of the linked list. So we will call this pointer a trap pointer, and we will go to a next element b. That means we will traverse to the node up to we reach this b, right? So that may be 1000 nodes or 1 million nodes, but we will just sequentially travel until and unless we reach to the node b. So we have reached b, so we stop here. Now we want to insert a new node, right? So we create a new node with the data as m, and we will point the next pointer of this node as c, and we will point the previous pointer of m as b. We will also do the last the c node's previous pointer back to m, and then b node's next pointer back to m. Basically we are trying to insert it between c and b, right? So these pointers are manipulated, and now we can clearly see the m has successfully been inserted inside our linked list, and this algorithm is clearly O of n, because to reach b we have to sequentially traverse from the head until we reach b. So removing an item is similar. First of all, we start from head, we reach to that element sequentially. Now we have reached it. Now we will do some pointer manipulations. First of all, we will make the just next pointers previous point to this earlier b node, because we are trying to remove m, right? And we will try to make this b's next pointer point to c, and then we can just remove trap at all, and this will clearly remove us. Actually this remove operations is frequently written as O of 1. That is because while analyzing the complexity of removal, we are assuming that the reference to the item to be deleted is already provided to us. If we consider finding as well as removing, then that is clearly O of n. But while analyzing the complexity of removal in most of the textbooks, and if you look upon the articles and in many literatures, you can find it as O of 1, because the removal itself is O of 1 and the finding is O of n, right? So I will explain you with an example. Suppose we have a doubly linked list here and we have a singly linked list here, and we are trying to remove the node C. Okay, in case of singly linked list, we are assuming for removal we are assuming that the reference to C is already provided to us. Okay, let us assume that the reference to this node as well as this node is already provided to us. So for doubly linked list, we can go to the previous node B, and then we can manipulate this pointer to just point to the next node after C, right? So we can just do this because we have this pointer pointing to the previous element. Starting from C, we can go back to B and then manipulate B's pointers, right? So if we have reference to C, we can go back to B, and also we can go back to D and manipulate this pointer to point back to B, right? So we have access to both directions, and then we can just remove it. No matter how many number of nodes are there in the linked list, the operation will always execute in O of 1 time. But let us consider the singly linked list case. Actually we have reference to C, right? But to remove C, we have to manipulate this pointer, this one. We have to make it point to just next element, that is D, right? So the next pointer of B should point to D. But starting from C, we have reference to C, right? We have no way of going back to B. We cannot go back to B because there is no link for going back to B. We cannot go backwards. So what is the solution? We have to start from head again, and then we have to go to the element just before C, right? So we have to traverse all of the nodes again, and then we go to B, and only we can just update this pointer. So only we can remove C. So for that extra traversal, this algorithm has complexity of O of n. So this is why I have said that the doubly linked list has the removal complexity of O of 1, whereas the singly linked list has the removal complexity of O of n. So what are the applications of linked list? The applications we can see are they are implemented, they are used in the implementation of stack and queues. Actually we can implement stack with a linked list, and we also implement queues with linked list. Actually queues are optimally implemented using linked list. Okay, we will discuss that later on. And while representing the adjacency list of representation of graphs, also manipulation and operations of polynomials and hash collision by separate chaining, we had discussed it earlier. What is hash collision? And I had said that there are two methods for resolving hash. One is by separate chaining, one is by probing, and while using hash collision by separate chaining, we will use linked list. So let us see how we can actually do doubly linked list. I will not actually implement all of these methods, but I will do few of them actually to show you how they work in Python. So let us go to data structures and create a new file called doubly linked list. So inside this, I will just copy the node I had from the singly linked list. But now, along with self.next, I also have self.prev. That means previous node. Okay, that is also node. Now I say class doubly linked list def init constructor So I will just say self dot head equals to none when we are initializing a doubly linked list, self dot tail equals to none, and self dot num items equals to none. So first of all, we will try to insert front. Okay, self item. So for inserting at the front, we will basically just try to check if the list is empty. Okay, So first of all, I will write a method for checking if the list is empty. Def is underscore empty self. What I'll do is I will return self.head equals to self.tail is equals to none. That means if self.head is the same as self.tail, which is also as the same as none, that means both self.head and self.tail is none. That means the linked list is currently empty, right? So I'm returning that. So inside insert front, I will first of all check if self.dot is empty. If it is empty, then I will basically say that I will create a new node with this item, and I will say self.head equals to node and self.tail equals to node. That means the newly created node is also head, it is also tail. Both head and tail are the same node now. I will put a comment here, create a new node. This is both head as well as tail. If the stack is not, if sorry, the list is not empty, then what we will do is we will create a new node with an item, and basically we'll try to say we create a new node. We will say node dot next will equals to self dot head, right? Because this node dot next, the newly created node will point to the existing head, right? And I will also have to say self dot head dot piv equals to this node, and finally I will say self dot head equals to node. What I'm trying to do is I'm first trying to create a new node here, and then I will say this new node's next will be pointing to existing head, right? New node's next pointer will be pointing to existing head, and then I will say existing heads pointer will be pointing back to the new node, because in the doubly linked list we will have to keep track of previous as well as next pointer. So if we say that A's next is B, then we will also have to say that B's previous is A, right? So we will have to look both of the way. So we say node dot next is self dot head, then self dot head dot previous is node itself, and we will basically say self dot head is node. Okay, I will define a display function, and then basically what I'll do is I will start from head trab equals to self dot head, and I will say while trab is not none, and then I will print trab dot data, and at the end I will put something like this to denote it is a doubly linked list, and trab equals to trab dot, basically I'm traversing in forward direction, right? Because I'm starting from head and then I'm going next. If I start from tail and come previous, then that will be backward traversal, but I won't do that. That is left for you as exercise. So trab dot next, and then basically if we have reached to the end of the list, we will just print, that means printing a new line there. Okay, let's test out this first function, doubly linked list dot py. So inside this, first of all I will have to input from data structures dot doubly linked list input doubly linked list, and I will say basically let's say animals this times. Animals equals to doubly linked list. I create a new doubly linked list and say animals dot insert front, and in the front I say cow, and I say animals dot display. If I run this, init is missing one required positional argument item. Oh, let's see, line number 3. Okay, doubly linked list does not need item as a positional argument. That is quite nonsense. I won't provide it. So let's run it again. Okay, here we can see cow is inserted, right? So if I say animals dot insert back and then buffalo. Oh, I haven't defined insert back. I forgot that. Insert front. Then in front of cow, the buffalo got appended, or it got inserted, right? So yeah, this is working. So let's go back to our code and let's insert another function here. This is insert front, and let's say insert back. Okay, if the node is empty, we follow the same procedure. So we just copied it and pasted it, just fixing the indentation here. Okay, if it is not empty, then what we will do is I will first traverse to the I also do not need to traverse actually while inserting to the back, because I already have tail pointing to the last node, right? So what I'll do is to insert at the tail, I will first create a new node. And then I will say tail dot next equals to this node, and node dot prev equals to tail, right? Because if we say tail dot next as node, we will also have to define node dot previous equals to tail, right? We have to define both of the relationship together. Raj Lamichani says, sir, hello sir. Technology channel says, good job Bikalpa bro. Thank you bro. How are you? Welcome to my channel. Okay, inside the where I was. Okay, I'm here. Insert back. So tail dot next equals to node, and node dot that is previous equals to tail. Okay, this is working, I think, both ways. Now we have to update tail, right? So I will have to say tail equals to node, because I have already inserted the new node at the end of the linked list. So I will have to basically point that tail pointer to the new node, right? Because the node that is that tail is now currently pointing, it is no longer the last node. We have already inserted a new node after that, so tail also needs to be it needs to be updated. So I save this, and let's go back and animals dot insert back. I try to insert snake. Let's see what happens. Okay, tail is referenced before assignment, line number 39. Let's see, line number 39. Okay, I always make this mistake. I cannot access tail from here. I will have to say self.tail, self.tail dot next, self.tail, and self.tail. Okay, if I run this, okay, buffalo, cow, and snake got added to the last element. That means it got inserted as the last node of our doubly linked list. So yeah, insert is working. So let's try removing the elements. Okay, def remove underscore front. Okay, for that I will actually try to remove from the front, and first of all I will have to check if is empty. If the linked list is empty, we cannot remove from the front. We will just return or raise a runtime error. I will say linked list is empty, and then if it is not the case, then what I'll do is I will have to remove from the front, right? So for that, save dot head dot previous, no, save dot head dot next dot previous. That means the heads next means the second element, and the second element's previous. But what if there is only one node? Yeah, that's quite problematic. Okay, let's try writing a case for that too. Elif save dot head dot next equals to save dot till. That means save dot head equals to save dot till. If the stack is empty, we will not come down to this this particular condition. But if save dot is empty is false, that means the list is not empty. Then we will check if head and tail point to the same node. If head and tail point to the same node, that means there is only one node in the linked list, right? So in that case, what I'll do is I will just say data equals to save dot head dot data. We are going to return this data later, and what I'll try to do is self dot head equals to none, because there was only one node and we already removed it, right? So it is none. Save dot tail is also none. There was only one node and we removed both of the nodes, then both of the head and tail pointers will be none. So this covers only one node case. And finally, let's see if both of these conditions are not valid, then I will do something like okay, I forgot to return data from here. Okay, because while removing I try to just return the data also. Okay, so if these conditions are not fulfilled, then what I'll do is I will just say data equals to save dot head dot data, and I will say save dot head I'll say self dot head dot next dot prev equals to none, and I will say self dot head dot let's say temp equals to self dot head, and I will say self dot head equals to self dot head dot next. That means head is just pointing to one element towards the right, and I will basically do temp dot next equals to null too. I basically do not think this is needed, but anyway, let the garbage collector do its thing, but I will just leave it anyway. So what I'm doing here is I will first take out the data in the head node, and that is a head pointers node, and I will try to reach the second node, and the second node will have prev equals to none, because if we remove the first node, that is the front node, then the second node will have its previous pointer equals to null, right? So I will try to store the reference to the first node in temp, and I will just move the head pointer to point to the second node, and then I will just say temp.next equals to none, and I will return data. There may be some memory leaks right here in the code, because we do not get everything perfect on the first try. But anyway, let's see what's whether this works or not. So remove front, right? I'll try to remove front. First of all, I'll try to print animals dot remove front. Okay, it removed buffalo. Was buffalo at the beginning? I'm not sure. Let's do animals dot display here. Okay, yeah, buffalo was at the beginning. I did remove front, then buffalo got returned back, and it got deleted from the linked list, and now cow and snake. So yeah, this method is working. And also I will remove back. I will have the same code from here. Remove back. If it is empty, we say linked list is empty. If there is only one node, then the similar case is there. But if both of these cases are not valid, then we will say data equals to save.tail.data, because we are removing from the back. So we will say save.tail.data, and save dot I will just remove these all. So now for removing the last node, we will have to point the next pointer of the second last node as null, right? So we will say save.tail, this means last node, dot prev, this will give us second last node, dot next, second last node's next pointer, this will equals to null. We will have to do this. And also what we will try to do is we will say save dot we'll create a temp pointer, temp equals to save dot tail, and basically I will say save dot tail equals to save dot tail dot previous, because I will just move the tail pointer to point to the second last node now, because we are removing the last node. And then I will basically say temp dot previous equals to none, and just return data. So let's see if this is working. I say animals dot remove back. In this case, snake should be removed, right? So let us see if this is working. Yeah, snake is removed, and we have cow and buffalo in our doubly linked list. So this method is working. So I won't cover the removal from the middle part of the linked list. That is for you as an exercise, because I can't just cover these all in planned time. So basically I will first teach you how you can actually find the algorithmic complexity of a particular method, as someone had asked earlier. So basically I will try to show you the algorithmic complexity of this particular example. So first of all, in this 44 position, if self dot is empty, right? So while calling this particular function, we will have to go to self dot is empty to find the algorithmic complexity. So it's just trying to access the head pointer, access the tail pointer, and checking if it is equal to none, right? So accessing the head is also constant time, accessing the tail is also constant time, and then checking is also constant time. We can do that instantly. So that is O of 1. Where were we? Here. Okay, this is O of 1. So now if this is the case, then this line will also be instantly executed. This will also have O of 1 complexity. Now we are trying to compare here. Self dot head is also O of n, O of 1, that is constant time. Self dot tail is also constant time, and basically everything we are trying to access here is available instantly, so that is constant time. So these all are O of 1, and in the else case also these all are O of 1 itself. So these all each and every statements are O of 1, that is constant time. So basically when we try to add them all, we will have something n times constant, some constant times O of n, right? So that means if there are 10 number of lines, that means 10 O n, 10 O1, right? So but what we can actually see here is we can remove the coefficient part of the big O notation. So we can remove the 10 part, so we can clearly see that this algorithm, a particular remove front algorithm, is O of 1. So we can say that is O of 1, O of 1. But let us see another example where I have displayed, yeah, this one. Okay, so this first operation, it is O of 1, right? Because we can just instantly access the head pointer from this self instance. But inside this loop, while trav is not none, we are actually traversing through each and every element of the pointer, right? So that means if there are n nodes in the linked list, we are running this loop for n times. So this selected part is O of n, and then printing is O of 1. That is simple. We can just execute this node pretty simple, straightforward. So this is O of 1 and this is O of n, but the overall complexity will be the larger, higher order complexity. That means O of n will be the complexity of this overall algorithm. So display is O of n, traversal is O of n. So in this way we can try to find the algorithmic complexity of a particular Python code snippet itself. So let's save this and let's go back to our discussion of the queue data structure. Swapnil Upadhyay says, hello Swapnil, how are you? We are discussing queue now. Actually queue is a first in first out data structure. The item that gets inserted in the beginning of the array, on the beginning will get removed out first. That means whatever actually, sorry for the delay, guys. My internet connection just broke and I was out for a while. So yeah, I was talking about queue and then we were talking about what queues are. Queues are first in first out data structures that follow FIFO order, and the first one to insert the first one to get inserted will be the first one to get removed. It is similar to queue at a bank counter, and you can see simulate that using a queue, because the first one to go to the cashier or the counter or the first one to sit on the line will be the first one that will get served, right? So we will see at the operations in queue. They are in queue, deque, and peek. In queue means to add the item to the end of the queue, and deque means to remove the item from the beginning of the queue. Peek means to return the item from the beginning of the queue without actually removing it. So let us see how these operations work. Suppose I want to enqueue F will go to the end of the queue. Suppose I want to deque, I will deque from the beginning, right? So if I enqueue G, then this will go to the end. So that means the element that will get inserted at the first will be also the element that will be removed at the first. So looking at the implementation of queue in Python, there are several ways we can implement it, and two of them are using dynamic array and using linked list. So we will see each of them, and the complexity depends upon the implementation, so we will try to look on the complexity on both of the cases. So while enqueuing and using the dynamic array, suppose let us see we are using a dynamic array here and we want to enqueue a element. So if I say using a dynamic array in Python, enqueue is equivalent to array.append. Yeah, append is available in Python's built-in list, and deque is equivalent to array.pop. That means popping out the first element. Pop 0 means popping out the first element. So if I say enqueue 12, then I can just go to the end of the end of the dynamic array and insert 12, and append operation has O of 1 complexity, so enqueue operation using the dynamic array will have O of 1. But if we consider the deque operation, it is not O of 1, but it is instead O of n. Because let us see the example. Suppose we are dequeuing from this array. That means we are removing the first element, right? Pop 0 means first element is being removed. So if we remove the first element, then we have a problem here. We actually have a problem that there is a hole in our dynamic array. So this needs to be get filled, right? Because there may not be a hole, or all the elements should be stored contiguously in dynamic array. So for that 23 needs to be shifted of 1 position backwards, and 67 needs to be shifted 1 position backwards, 56 and 12, these all of the elements should be shifted 1 position backwards. So that is why this algorithm is O of n while using the dynamic array. But if we consider using a linked list and we maintain a head as well as a tail pointer to the linked list, then enqueue operation is equivalent to inserting at the tail. That means inserting at the last. We already have a reference to the tail, so inserting at the last will be a constant time operation. And dequeuing operation is equivalent to deleting from the head, because we can do that in O of 1 time, that is constant time, because we already have a reference to head pointer. So let us see how we can deque using a linked list. So for that we already have a reference to a tail pointer. For that actually we already have reference to head pointer. Sorry, for dequeuing operation we are actually removing from the head, right? So we just basically move the head to the second node, and then we just remove temp, and that's it. We can do that in constant time, because no matter how many number of elements are there, how many number of nodes are there, we can just delete that in constant time operation. So that is O of 1. But similarly enqueue, for enqueue we already have a reference to tail pointer, so we can just insert a new node and then make the tail pointer tail node point to the new node, and just shift the tail pointer back to the new node. So this is also a constant time operation. We already have the reference to tail pointer, so we can do it in O of 1 time. So using the linked list we can actually implement queues optimally. So queues have enqueue operation will have O of 1 time, deque operation have O of 1 time. That is when optimally implemented, right? So if you implement it using dynamic array, then you cannot achieve this complexity. And peaking is also O of 1, because we are just accessing the element. So let us see how we can implement a queue using the linked list. So in this case let's go to data structures and create queue.py. Okay, here what I'll do is basically I will create actually I will show you how to implement queue using the dynamic array as a dynamic array first, right? So first of all, if I say queue equals to a list, so whenever I want to enqueue to this queue, I will just say queue.append, and I will append something 5464, and then I will append anything another thing here, dot append 23. So if I try to print q, so this will get printed. Now if I want to deque operation, that is equivalent to doing, I will print it q dot pop 0. If I do q dot pop 0, then this is equivalent to dequeuing an element. That gives us 4564. If I try to print q afterwards, this will be only 23, right? So this is using the dynamic array. But if I want to use a linked list to actually implement a queue, I will actually want to use a doubly linked list to actually implement this queue here, because I have quite less time to actually modify this linked list code to insert, to actually add a tail pointer in this linked list. But actually if I use doubly linked list, then I already have head and tail. So enqueuing operation is equivalent to inserting at the back, and dequeuing operation is equivalent to removing from the front. So what I'll do is I will basically try to create a class queue, and in constructor what I'll do is I will create save.list save.items, let's say, is a linked list, right? So for using linked list, I will first have to input it. So from data structures dot doubly linked list, import doubly linked list, and then save.items equals to doubly linked list. Okay, and I will just define enqueue as the operation, save.items dot insert at back. Here I will need an item also. Okay, and save def deque save.items dot I will have to return, right? So return save.items dot remove from the front, right? Insert at the back, remove at the front. So item, I will say def is empty. If the queue is empty, I will just return save.items.isEmpty, because I have already implemented isEmpty method inside the doubly linked list. So yeah, this will be all. I think I'll go to examples, create a new file called q.py, and I will say q equals to new q. But first, for using this q, I will have to import it, right? So from data structures dot q import q. Okay, basically I will add another method here too, that is def display. I want to display the q also. What I'll do is save.items.display, because I have already implemented display method inside the doubly linked list, so I will just reuse that. So first of all, I created a queue, and then I will enqueue 78. I will enqueue 76. Okay, and if I do q.display, I will be able to view that 78 and 76. But if I want to print q.deque, that means the first element, that is 78, will be popped out, right? So let's see, deque is missing one positional item. Okay, deque should not get item. remove front also should not be provided with item. Actually it is removing from the front, right? So let's run this. Okay, it gives us 78, and if I do q.display afterwards, here I will clearly see only 76 is there. We have already popped out 78. So yeah, this is how you can implement queue using the doubly linked list. Actually we have used the doubly linked list, we have already written, but actually in Python, when you are using Python, most of the time the thing you need is already implemented in the language. So the doubly indeed linked list as well as doubly indeed queue is already implemented in collections library. I will talk that later. First of all, I will go to my slides here, and first of all talk about deque, that is double indeed queue. Actually deque is quite similar to the queue, but in it we can insert as well as remove from both of the ends. In the queue actually we were able to insert from the back and remove from the front, but in the deque we are able to insert as well as remove from both of the ends. And this can be simulated easily by using a doubly linked list, because we have already seen that doubly linked list also has remove front, remove back, insert front, insert back, right? So this can be simulated using a doubly linked list. If we simulate the deque using doubly linked list, then remove front will be similar to remove front of the doubly linked list. Remove back of deque will be similar to remove back of doubly linked list. Add front of deque will be similar to insert front of the doubly linked list, and add back of the deque will be similar to insert back of the doubly linked list. All of these complexities are of O of 1. That is quite awesome. And in the Python standard distribution, we have already I had already mentioned that we already have collections.deque module, and that this deque module already provides the implementation of doubly indeed queue. I will show you how. Collections.deque has these operations: append item, this will add to the right end of the deque; append left item, this will add at the left end of the deque; pop will remove the item from the right end of the deque, and pop left will remove the item from the left end of the deque. We can see the applications of queues here. Actually it is very useful for simulation of the real world queues in programming, and also resource sharing in operating systems, first come first serve basis, process scheduling in operating systems, again first come first serve, that is FCFS algorithms use queues, and breadth first traversal of trees and graphs use queues for implementing them. Actually I think we won't be able to cover that in this video, so we will cover the trees and graph traversals in the second part of this video. I will do that sometime later in this month. So let us go back and see how the doubly indeed queue is implemented in the Python library itself. So for that I will create a new file here, deque underscore built-in .py. Okay, from collections dot deque, from collections input deque, and now we will create a doubly indeed queue as queue equals to deque, and we pass in the value of the initial list, right? So if I say 12 and 23, now my new deque is created, and this will be stored in the object queue. And if I say queue, if I say print queue, it will print a deque 1223. Now if I want to add at the last at the end of this queue, I will say queue.append 88. This will add 888 at the last. If I say queue.append left and 99, this will append at the beginning of this deque, right? 99. And also similarly, if I want to say queue.pop, this will remove from the end of the queue. Right, 888 got removed. And if I do queue.pop left, then it will remove from the beginning of the deque, that is 99 will get removed. Yeah, 99 is removed. So yeah, this is how we can use deque module from the collections deque module from the collections module, right? Deque is actually a class, deque class from the collections module. So yeah, this is already implemented in the Python itself. So yeah, actually I was planning trees for this session too, but I think this session is already so long, so I think I will have to pause the session for now, and and give some time for a Q&A session. So I will basically do a few minutes for Q&A session. If you guys have any problem with the today's session, I will answer your questions, and then we will end this stream. So if you guys have any problem regarding this session, please you can ask the question now in the comment section. Let's read out the comments. Who is here? Swapnil Upadhyay says Sai Sadai. Hello Swapnil. I think it's already 8 p.m. So yeah, we are getting quite late. So we will implement the rest of the data structures in the next session. So we will end this session here. So everyone, stay safe.